We discuss in this video about Boolean matrices. This topic is going to bring us one step closer to the foundational definitions that we need to discuss when we go to finite automata. So Boolean matrices, they are matrices over elements 0 and 1, and we are going to do operations with 0, 1 as defined in the Boolean algebra B2. So we are going to work with B2, and I just recall that B2 was a algebra over the set of elements 0 and 1, and we had an addition operation, we had a multiplication, we had a negation operator. 0 was the 0 element and 1 was the 1 element. And I just recall how these operations were defined. So plus was defined as in this matrix, 0 plus 0 was 0, and all the other elements were 1, including 1 plus 1 is equal to 1. The multiplication was defined to be 1 times 1 is 1, and all the other ones were defined to be 0. And the negation was defined to be negation of 0 is 1, and negation of 1 is 0. So the definition for a Boolean matrices is that this is a matrix with, say, m rows and n columns. I'm going to just show the dimension of this matrix here. So when I'm writing m times n, what I mean is that it has m rows and it has n columns. And all of these elements, A, I, J, they belong to the set 0, 1 for all i's between 1 and m, and all j's between 1 and the n. So we define some operations on these matrices in the following way. We have two matrices, A and B. Matrix A with elements Aij, and matrix B with elements Bij. They are all matrices of the same type, so m times n. We call this m times n the type of the Boolean matrix. So having these two matrices, we define their sum. So their sum, denoted by A plus B, is defined in the following way. The ij entry of the sum is obviously going to be defined as the sum of the ij entries of matrices A and B, just like it's defined on the usual sum of matrices. The product is defined, however, in a different way than what you might be used when you discuss about products of matrices. And it's no surprise that it should have a different definition, because in fact, having types m times n for A and B doesn't allow you to operate with the usual product of matrices. So we define this product, and I'm using even a different sign just to point out that it's not the usual product that you know in terms of matrices. So this is going to be the dot product, but I come back to the name of this operation in just a moment. This is going to be defined simply as the ij entry being the product of the ij entries of A and B. And remember, plus and dot, these are the operations that we define on Boolean algebra B2. So this product has a name. This is called Hadamard product. It's also called a Schur product. And obviously, this is also called element-wise product. Just like the definition is suggesting that the product is done really by multiplying the corresponding elements from A and B. And finally, I also define the bar operator. So the bar of matrix A, it's a matrix of type Mn, just like A. And the ij entry is going to be, as you might expect, the bar of Aij, so the bar of the ij entry of matrix A. So all of these operations that we have used to define our matrix operators, they are operations on Boolean algebra B2. And I give an example right away. So example. If I take matrices A to be one with 2 rows and 3 columns, and for example having these entries, and I take matrix B to be of the same type, 2 rows, 3 columns, and with entries like this, 0, 1, 0, and 1, 0, 1. So for example, then the sum A plus B is going to be, by definition, a matrix of the same type, 2 rows, 3 columns, and each element of the sum is going to be the sum of the corresponding elements of A and B. So for example, in this corner, I take 0 plus 0, and that's 0. 0 plus 1, that's 1. 1 plus 0 is 0. 1 plus 1, remember in B2 this is equal to 1, and so on. And we have the element-wise product of these matrices. This is a matrix of the same type, 2 rows, 3 columns. And again, I'm just multiplying B2, the elements, the corresponding elements of A and B. So if I have to calculate this top left corner, this is going to be 0 times 0 in B2, so that's 0. Then it's 0 times 1 in B2, that's 0. 1 times 0 is 0. 1 times 1, that's 1, and so on. And finally, if I want to calculate also a bar, matrix of the same type, and I simply take the bar of each one of these elements, and I'm just writing it here. So that's going to be 1, 1, 0. So the bars of the first row of A, and the same thing on the second row. This is going to be 0, 1, 0. I go back to the definitions, and as you might expect, I define now a 0 matrix and a 1 matrix. And the 0 matrix of type M times N, so M rows and N columns. This is going to be denoted as 0, and I'm just writing the type. And obviously, this is going to be the matrix having just 0 elements on all the entries. And at the same time, I define the 1 matrix, again of type M times N. And I denote this by 1. I show the type. And this is the matrix having 1 everywhere on all of its M times N entries. And with these definitions now, there is a lemma that I think is going to be intuitively obvious to you, and I don't even go into proving it because it all goes to the similar properties of the Boolean algebra B2. But the property still is worth defining, and it goes like this. If I have some numbers Mn, at least 1, then this set, by the way, I will just introduce one more notation. Maybe I'm writing the lemma and then I introduce this notation. So the notation that I should have introduced, but I introduce in a moment, is this BMN, which is really the set of all I'm just writing it here. So B, M, N, this is the set of all Boolean algebras of type M times N. So if I take all these Boolean algebras of type M times N, and I take the sum that we have just defined, we take the element-wise product and the bar operator, and we have this zero matrix of type M times N and a one element of type M times N. So this structure is, as you might expect, is a Boolean algebra. And obviously it's a finite Boolean algebra because I only have M times N entries, and each one of them can only have two different entries, 0 or 1. And so altogether, this is a Boolean algebra with exactly 2 to power M n elements. So as a result, I don't prove it here. To prove it, you just have to check all the properties B1 to B10 in the definition of a Boolean algebra, but all of them are collapsing to checking similar properties for the Boolean algebra B2. So in that sense, it's going to be just a simple check that indeed all the properties for matrices collapse to the similar properties of B2. So nothing really too sophisticated to prove in this respect. So what we had so far was this Hadamard product or element-wise product, but as a matter of fact, on Boolean matrices, you can define also the usual matrix multiplication, and it's often useful to have this product in different applications in automata theory. So I'm going to define this usual matrix product now, and I do it like this. I will take one matrix A of type M times N, so a Boolean matrix of M times N, and then I also take another matrix, but this time is going to be of type N times P, as you might expect, so I can define the usual product of matrices. So these are Boolean matrices. And I define their product, AB. It's really going to be, so A times B, if you like. So this is going to be a matrix of type M times P, just like you have in the usual matrix multiplication. And it's defined, the ij entry of this matrix is defined in the following way. This is going to be sum from k equal 1 to n of aik times bkj. So just like you normally have with matrix multiplications, I'm only pointing out that this dot, this multiplication, this sum, these are operators in the Boolean algebra B2. So here is an example. So if I take a matrix A to be of type 2, 3, so 2 rows, 3 columns, and for example, I take 0, 0, 1, 1, 0, 0, and I take then matrix B to be a matrix with 3 rows, and for example, 3 columns, or 4 columns, I'm going to have 1, 0, 1, 1, 0, 0, 1, 1, and 0, 1, 0, 1. So I'm just pointing out the types just to make sure that we can indeed do the standard matrix multiplication. So this is a matrix of type 2 times 3, and because this one has 3 columns, this one must have 3 rows in order to have the product, and indeed it has 3 rows and 4 columns. So the product AB is going to be a matrix that has 2 rows, just like A has, and 4 columns, just like B has. And this can be calculated element by element. I'm just writing down the result, and then I'm going to check one element to show you how the calculation goes. But the full result that you can also check element by element is going to be this 0, 1, 0, 1, and 1, 0, 1, 1. So I check just one element. For example, if I check this bottom right corner, so that's going to be our element on row 2 and column 4. So this one is going to be, by definition, sum from k equal 1 to 3. I have 3 columns in A and 3 rows in B. So this is going to be the sum of A to K times B K4. So what this means is that we are going to take the second row and of A, and we are going to take the fourth column of B, just like we normally have in matrix multiplication. So this is going to be 1 times 1 plus 0 times 1 plus 0 times 1. And that's going to be 1 times 1. This is 1 in the Boolean algebra. 0 times 1 is 0. 0 times 1 is 0. And when I make this sum, this is going to be 1, just like I have announced in my example. I define now also the transpose. So this was one definition I had on this whiteboard. And now I want to define also the transpose. Transpose of a matrix. Transpose of Boolean matrix. A of type m times n. This is going to be denoted as a T, a transpose, and it's going to be a matrix of type n times m. So the type is exactly reversed as in A, and each one of these entries, Cij, is going to be exactly a Ji for all I between 1 and n, and for all j between 1 and m. And that's exactly the usual way that the concept of a transpose of a matrix is defined. So no surprises here. One more concept I want to define. I want to introduce a notion of partial order. So on Boolean matrices. So partial order. I'm going to just say that A, so 2 matrices, if I take 2 matrices, Aij of type m times n, and B also of exactly the same type, m times n. So these are Boolean matrices. So I'm going to say that A is smaller than or equal to B if and only if we have that Aij is smaller than or equal to Bij for all I and j. So in other words, if all the elements are in this order smaller than or equal to with the corresponding element in B, then I'm going to say that A is smaller than or equal to B. Now remember that all these elements, they are on set 0, 1. So when you think about this, what are the conditions under which you have this smaller than or equal order? Just because you are working with the Boolean algebra B2, just because you are working with values 0 and 1, this is also easy to see that it's equivalent with saying that Aij is 0 or Bij is 1, and this should hold true for all I and j. So this is just an observation that holds because we are working with the Boolean algebra B2. There is only one more observation I want to make, and that's really about some general properties on matrices having to do with associativity, distributivity, and a couple of other things. And to do that, I just have one preliminary result, and then I formulate this result for Boolean matrices. So the preliminary result, before I show you the main one, the preliminary result is the following. It's in general about Boolean algebras. So I'm saying for a Boolean algebra, so not just Boolean matrices or B2, but really for any Boolean algebra B, then we have the following property: A times a finite sum of elements is exactly this sum, which is just a generalized distributivity law. We had it defined previously for just a sum of two elements, but in fact, obviously this holds true for any finite sum. And if you want to be orthodox about it, this could be proved by induction by n. And the other form of distributivity in Boolean algebras is A plus, and I have this product from 1 to n by bk. This is going to be product from 1 to n of A plus bk. And again, we had this proved for products of, or we had this defined as a basic law of Boolean algebras for products with two elements. And from that, it follows from, it holds for any product up to n. And you could show this by induction by n. So these are just general properties that hold for any Boolean algebra. And with these fixing of basic properties, I'm ready to define the main result I wanted to show for Boolean matrices. And this is the lemma. In your lecture notes, this is lemma 2.33. And what this says is A, B, C Boolean algebras. And I'm just going to say of a suitable type, so I don't have to specify here, but of suitable type for each of the properties that I want to define now. So this lemma says if you have these Boolean algebras, then the following properties hold true. So number one is associativity. So A times BC, and do note that I'm talking now about the usual matrix multiplication that we have just defined on Boolean matrices. So this usual matrix multiplication, this is associative. So this is about associativity. Second property is A times B plus C is A times B plus A times C, and this is obviously about distributivity. Then we have property 3, which says if you apply transpose twice, you go back to your original matrix. So this is double transpose. So double transpose is the same as the identity mapping. The fourth property is that the transpose of the sum is the sum of the transposes. So transpose sums. And finally, the last one that I wanted to formulate here is the transpose of a product. This is exactly B transposed times A transposed. So this property has to do with transpose. So I want to just prove for you property 1 and 4, and the other ones, they will be left for you to prove during one of the next demo sessions. So I'm going to prove 1 and 4. So to prove 1, I will just take an element from this left-hand side matrix, and I'm going to show that it's exactly the same element on the corresponding position for this matrix. Now, just so that these operations are well defined, obviously A has to be of some type m times n for some m and n. And then B has to be of a matching type because I will have A times B. So it's got to be n times something, for example, n times P. And C, because I'm multiplying B and C has to be P times something, for example, P times Q. So they have to have the right types in order for these operations to be applicable. So now in this situation, we have that obviously B times C is of type n times Q. And we have that A times B is of type M times P. And then the matrix on the left-hand side is of type, so it's A times BC, so that's M times Q. And the matrix on the right-hand side, so A times B was here, M times P, and P times Q, so altogether it's M times Q. So the types of the left-hand side and the right-hand side, they are the same, so we have a chance of proving this property. So now I'm taking an element of this matrix, and I'm going to show that it's exactly the same as the corresponding element of this matrix. So if I'm taking element of the matrix on the left-hand side, so this one, element ij, and obviously in this case, what I mean is that I is some element from 1 to m, and j is an element from 1 to q. So this is by definition the same as saying it's a sum of, and remember A was of type m times n, so this is going to be sum from 1 to n of A I k times the element in the product BC on position k times j. And now we have to think about what's the definition, what's the element on position kj of this product. So this is going to be it's going to be sum from 1 to n of this, what we had before, and this was now a sum of, remember, B is of type n times p, so this is going to be sum from 1 to p of bkp times cpj. So now this goes to being sum from k from 1 to n, and I bring this a inside, so this sum goes outside here, so this is going to be sum L equals 1 to p of AIK times this product, BKP times CPJ. And so the crucial observation now is that we are working in Boolean algebra B2, so the multiplication is associative, so I can move, in fact, the parentheses to have first this product, A times B, and then multiplied by C. So the sums remain the same as before. K equals 1 to N, L from 1 to P, and the observation is that I can do this multiplication in this order. First A and B, and only then multiply by C, Pj. So now what I can also do is I can just arrange these sums the other way around, and there is a point I want to make about that. So this is the same as saying first I do the sum from L from 1 to P, and then when I have the sum with K from 1 to N, as it turns out, I can have CPJ as a common factor of this sum, because it doesn't depend on K. So I can arrange my terms like that. And now you can observe that this is about some element of the product, of the matrix product A times B. So this is the same as, the sum remains the same as before. So this is a sum from L from 1 to P. And this is the element of AB on position IP, and then multiplied just like before with CPJ. And so by definition, what we have here is that this is really the element of this matrix on position IJ. And so that's exactly what we wanted to prove. We just got that A times BC is equal to AB times C. And that's exactly what the first point of our lemma was claiming. So that concludes the proof of the first property defined in this lemma. And so now to prove also the fourth property, which was the transpose of sums. So to do that, so the property that I want to prove now is A plus B transpose is A transpose plus B transpose. So in this case, for the sum to make sense, A is a matrix of type M times N, and B has to be a matrix of the same type, M times N. And obviously this means that the transpose of A is going to be a matrix of type N times M, and the transpose of B is going to be a matrix of N times M. Just to be orthodox about it, the type of A plus B is the same as the types of A and B, so M times N. And the type of the transpose of A plus B is N times M. So we have a chance of this sum being really exactly as the lemma claims to be. And we can establish this in a very easy way. We just take the matrix on the left-hand side, and we think about what could be the ij entry of this matrix. And A plus B transpose is a matrix of this type, so N, I is from 1 to N, and J is from 1 to M. So what we have is that by definition, this is the element Ji of A plus B. And by definition of the sum, this is the element Ji of A plus the element Ji, I'm sorry, Ji I should have written. So Ji of B. And this, if I think in terms of the transpose matrix A T, this is the element Ij by the definition of transpose. And this is plus. Same thing if I think in terms of transpose of B, this is the element ij of the B transpose. And this by definition is going to be exactly A transposed plus B transposed, element ij of this matrix. So that's exactly what we were hoping to get. The ij element of this matrix is exactly the ij element of this matrix for all ij. So that establishes that indeed A plus B transposed is equal to A transposed plus B transposed, just like the property 4 was stating.